In this video, I will be explaining the problem packing rectangles. So in this problem, we will have 4 rectangles, and then we have to somehow arrange them in a few possible layouts, so then we'll have a total enclosing rectangle. So basically, that way we can find the smallest enclosing rectangles. So here, since there are only 4 rectangles, what we want to do is test out all of the possible layouts. And yeah, it's the possible layouts are already given to you here inside this image. So let's take a look at this example input. So I drew out the rectangles here, and this is the first layout where we just put every rectangle side by side, and when we put them side by side, we see what is the total, the maximum area that we need. And then the second possible overlap of the layout will be putting one of the rectangles on the bottom and then everything else on top of it. Or to give you a better visual, we can take a look at, for example, if we put this one at the bottom instead, we could have these rectangles on top, while this biggest rectangle stay on the bottom. So this is the second possible way. And the third layout is once we still have one on the bottom, but we only put 2 of the rectangles on top of this current one at the bottom and leave one outside. So for example, here we could have one outside here and 2 on here. Then another possible layout, these two are basically the same thing because it's just one rectangle on top of another and then 2 other rectangles just standing on the side. So for example, here we could have move this out, and then this basically what this is depicting. We have 2 rectangles standing here, and then one rectangle on top of another one. And then for the final case, it's when we have one rectangle on each of the other 2 rectangles. So for example, we can have the rectangles arranged like this, one on the other one, just like this. So the first few cases are very easy to find. So the first one, we will basically sum up the total width and get the maximum height. So that will give us the dimensions of our smallest enclosing rectangle. So here, this will be our code. So this function will try out all of the possible combinations. So this is the case 1 when we have this layout 1. And when we have layout 1, we basically just sum up all of the rectangles, the width of the rectangles. So I stored these rectangles in pairs, and the first element of each pair will represent the width, and the second one will represent the height. So then for the height, we should get the maximum height, because here we're basically looking at the maximum height, so then that way our enclosing rectangle should have that height. That way it will contain all of the other rectangles as well. So this is case 1. And then for case 2, we basically do the same thing, still sum up the width. And here we're only looking at the top 3 first. We sum up the width and compare it with the width of the bottom rectangle. And we see we get the maximum width of these two, the top 3 rectangle or the bottom rectangle. And then for the height, we will add the height of this bottom rectangle to the maximum height of these 3 rectangles on top. So here I would sum up all the widths of the rectangles except the first one. So here we can think of the first rectangle as being on the bottom one. And still sum up the width and get the maximum height for these 3 rectangles that are on the top. And then we should compare that width that we just summed up with the width of our first rectangle. So this first rectangle is the one on the bottom. And we should get the maximum of that, so this way we can contain all of the rectangles. And then finally, we should add the height of our first rectangle to the maximum height of these 3 rectangles, because no matter what we do, since we're putting the 3 rectangles on the top of this current rectangle, the height of this current rectangle will always be added into this total height of the enclosing rectangle. And then for this case, for the third case, we're basically summing up the first. Actually, we're summing up the middle 2 I can think of this one as the last rectangle, so we will leave this out and only add these two rectangles. So we have rectangle 0, rectangle 1, rectangle 2, and rectangle 3. So we should add up rectangle 1 and 2 and leave 0 and 4 out, 0 and 3 out for now. And so first we will still add up those two the width and also get the maximum height. And then so here is the first part, we'll get the width. So I will get the maximum width of the sum of these two top rectangles and the width of this bottom rectangle. So the top two rectangles are these two rectangles, and the bottom one is this rectangle. So we will get the maximum of that. So this will give us the smallest width needed for this side of the rectangle. And now we should look at this one extra rectangle. And to get our total width, we should just add the width of this fourth rectangle into our maximum width that we just got. So this is what I did here. We'll add the final width of the final rectangle to our maximum width. And then for the height, we basically do the same thing, but here we're, for these three rectangles here, excluding this last rectangle, we will still do the same thing for this previous one as well. Get the maximum height and then add our height of the bottom rectangle to it. So the maximum height will be, so we can get the maximum height by finding the maximum of these two top rectangles and add the height of our bottom rectangle. And then we should compare that height that we just got with the height of our last rectangle. Because if our last rectangle is taller than that, then no matter what we do, we still need to have a rectangle that is at least the height of that tallest rectangle. So we'll get the maximum again, and we'll use this check function again to check whether this is smaller than our previous answers. And then we will look at test case 4 and 5. So these two cases, because they're basically the same thing, we can ignore this one. Let's just look at this fifth case. So the fifth case is when we have one rectangle on top of the other, and then the other two rectangles are on the side, so basically not on top of the other two rectangles. And here we will get the maximum width of the first two rectangles, so basically this side, and this way we can get the width of these two enclosing rectangle. So the enclosing rectangle for these two rectangles on the left will have a width of the maximum width of these two. And then for the rest of the width, we have to add up the width of the third rectangle and the fourth rectangle, because here no matter what we do, we're always leaving them on the side, so their width will always be included inside our enclosing rectangle. And then for our height, we will get the maximum of a few of these height. So the first height will be the height of the two rectangles on top of the other one. So this height will be the height of this bottom rectangle plus the height of the top rectangle. So this will give us the height for these two rectangles add up together. And then we'll also need the height of the third rectangle and the height of the fourth rectangle. So here's the height of the third rectangle and the height of the fourth rectangle. And now we get the maximum of all of those. And this will give us the height of our enclosing rectangle. And then for the final layout, this case is a bit more special because we can have a few different situations here. And so generally we'll see what happens if one of the rectangles is on top of the other one, and this same applies for the other two. So here our width, we know that it will be at least the sum of these two, or the so it will basically be at least the sum of these two or the sum of these two. So we should get the maximum of these two sums. So we should get the width of these two rectangles on the top added up together, and the width of these two rectangles on the bottom added up together. And we get the maximum of that. So that will give us the minimum width that we will need for this situation. And so here, this is what we do first. We will get the total sum of the width of the rectangles. And also here, we don't have to look at the total sum of these two rectangles on the top at first. This is because, for example, we can have these two cases when we have one rectangle here, and then we have another rectangle here. So let's say we also have one here, and this rectangle can extend to some other positions. Let's just say it extends all the way here, and this rectangle will extend, let's say, all the way here. Then here, we're still putting these two rectangles on top of the other one. And so in this case, they will give us the maximum width of the enclosing rectangle. But there will be other cases if one of the rectangle, for example, this one is taller than the other one, then this way we can somehow put these rectangles on top of each other. So for example, we can do it this way. And let's say the rectangle is only at this width. So normally, if we add up the width of these two rectangles, we will see that it's the maximum. So here, at first, if we add those two up, we will get the maximum. But we can have situations where this rectangle goes all the way here. So we have basically these two are still the bottom two rectangles, but one of them is very tall, and then so this way, as long as it's taller than the height of these two rectangles added up, this will make sure that this will give us the possibility to overlap this topmost rectangle on top of the other ones. So here, although the sum of these two topmost rectangles added up together will be this long, so this will be longer than the sum of these two widths. But here we can put one rectangle here and another rectangle on top. So this way we can still save some of this width starting at this point to this point. So this will save us some width, and we don't have to use that much width for this rectangle. So, but here we know that we'll definitely use at least the sum of the width for these two bottom rectangles, because we know that they're already touching each other like this way. So they're beside each other this way definitely. So they will definitely have a width of at least this long. And so here, this will be the width for that. And also here, we should get the maximum width for these two widths on the top. So on the top rectangle, because even if we have a situation like this, so here we can still have a situation where these two bottom rectangles have a difference big enough for one top rectangle to fit in between. But here we have another top rectangle that is way too long for the width of these two added up together. So no matter what we do, this whole enclosing rectangle will at least have a width of this whole width for this top rectangle. So this is what we get here, the width for the top rectangles. We have to get the maximum of that as well, basically get the maximum of all of these. And then for the height, we do, first of all, we will check the height for if we add the one rectangle on the bottom to the height of the other rectangle on the top. And so since we have two rectangles this way, we have one rectangle here on this top, like these two, and we also have two rectangles like here. So we should get the maximum of those two heights. This is the first height of the first two rectangles that are on top of each other, and then this is the height of the second one. And now we check the same thing so we check for some special cases like these. And first of all, we will have to check for these widths. And for this width, we will see what happens basically if we put one rectangle here in between these two. So we can have another case where let's say we put this rectangle here, and we have this rectangle on top. So here, when we have this case, then the width of our enclosing rectangle needs to be sum of the width of this first rectangle on the bottom and the rectangle on the top. But this is the other rectangle that's on the top, because the original rectangle that's on the top of this current rectangle that we're looking at is this rectangle over here. So we should get the width of these two rectangles instead. So the width of this current bottom rectangle added up with the other rectangle that's on the top. So this rectangle is on top of this other rectangle at the bottom. So we should look at these two, sort of like looking across the diagonals. And so this is what we did here. We should sum up the width of these two to make sure we have the maximum enclosing width. And also here, this is when we check for the special case where we can overlap one rectangle, or we can overlap the width of the rectangles. Like in this situation, when we have this width that is big enough for the whole rectangle. Let's say this rectangle is only this long. Okay, so for this case, we will have to first make sure that this height of the rectangle over here is longer than the sum, longer than or equal to the sum of these two heights. So these two rectangles added up together should have a height less than or equal to the height of this rectangle on the bottom. And so this is what we do. We subtract the height of the two rectangles on the bottom. So this gives us the distance between their heights. And we check if the height is smaller than the rectangle, the height of the rectangle for this one. And so if it is smaller than the rectangle for this one, then this means that there's might be some cases where we have a height like this. So we have a height like this. Then this way we will still put this rectangle on top of this other rectangle. So still put it like here, but this way we'll have to combine the width of these two rectangles. And so when we have situations like this, we must get the maximum of the sum of these widths as well, because now we have these two rectangles that are now like this. We don't have to look at situations like this because we've already visited some situations like this, and this is basically the same as one rectangle on the bottom with two rectangles on top and another rectangle on the side. So this is basically the same thing as this third case, but it's flipped over a bit. So we can think of this as the rectangle on the side, like this rectangle here, and then these two rectangles will be these two rectangles on the top, and then this bottom rectangle will be this rectangle. So we don't have to look at this case because we will already cover it in the other situation. So we should only look at this case when we have these directly on top of each other, and then we should get a sum of the width for these two, because here we have this part where we must put this on the side of we must put this rectangle beside the other rectangle that's on the top. So in this situation, we cannot put it on top of the other rectangle on the top. We have to put it at this position. Then this way we'll have to get the sum of their width and compare that with our maximum width. So this is what we did here. We will get the sum of these two rectangles on the top. So this is the width for those two. And then we get the maximum width for that again. And then the other situation is when we have the two bottom rectangles swapped instead. So when the first rectangle is so basically, this is the other case when the first rectangle has a height that is smaller than the second rectangle on the bottom. So we're going to have a situation like this. So this is still the same thing, but here we'll look at a few different items. So in this situation, we're adding up these two rectangles now. And when we're adding up these two rectangles, their indexes are different from these two rectangles. So here we can add up the other rectangles with the other two indexes instead. So here, for this one, first one, we're adding up rectangle 0 and rectangle 3. So 0 is the rectangle that's on the bottom, and then rectangle 3 is the rectangle that's on the top of the other rectangle. And then here, rectangle 1 is the other rectangle on the bottom, and rectangle 2 is the rectangle that is on top of rectangle 0. So we're adding the diagonal width for these two. And then still do the same thing, but here we still get the distance between them and check if that is smaller than the rectangle 2's height this time, because we're looking at two different ones. For example, we can have a situation like this. This way we can still overlap. So this way we can still put this rectangle that's on the top over the other ones, but then when we have different situations, this will change. So we should look at the other rectangles. And then we still, so if the distance is smaller than that, smaller than the height of this rectangle, we will still get the width, the maximum width of these two top rectangles added up, because if that happens, we're still combining the width of those two rectangles. So at the end, the result will still be the two widths added up together. And then here I will have this check method to find the minimum area. And here we only want to print out the ones that have the answers that have a width that's less than the height, less than or equal to the height. So here I first check if the width is greater than the height. If it is greater than the height, we should swap the width and the height. And also we should prevent ourselves from repeating the visited width and height already. So if it's already visited, if these two width and height are already visited, then we should just stop this check method. We don't have to check it again. Otherwise, we will set it to visited. And here the total width and height maximum will only be 200, because here it mentions that each side of the rectangle is at least 1 and at most 50. So we can have at most 4 rectangles with side length 50 added up together, so that will only give us 200. So here we'll set it to visited and get the area by multiplying the width by the height. And now we check if that is smaller than our minimum area that we got from previous layouts of these rectangles. And if it is smaller than the best area that we've got, then we will set our best area to this current area that we have. And also we should clear our answer vector and push back this pair into this width and height into our answer vector. So we'll print out the answer vector at the end. And the other case is if the area that we just got is equal to the minimum area. If it is equal to the minimum area, this means that it's also possible to reach the minimum area by using these two width and height. So we should also push that into the answer, but we don't need to clean the answer vector, because it still has the same area as our minimum area. And of course, if it's greater than the minimum area, we can just ignore this and do nothing. So we'll use this check for each of these cases and just put in the width and the height. And so finally, what we need to do is find the possible layout of these cases, because for this case, if we just do this, we will only look at one rotation of the layout, and there are multiple rotations. For example, you can flip some of the rectangles. For example, here we can, instead of having a rectangle that looks like this, we can rotate the rectangle so then it becomes something like this instead, but it still has the same width and height, but just flipped over. And also, we can arrange them in different orders. For example, we can put this one on the bottom and this one on the top instead, or a few other cases. So what we can do is, for the rectangles, of course, we can use the permutation function, the next permutation function that's already implemented in C++. So we can always get the next permutation of this current rectangle width and height. And every time we get the permutation, we will use recursion to rotate some of the shapes. And to do that, we will use C to keep track of the total rectangles that we've already modified. So we can try, if we've already modified 4 rectangles, then we will try the rectangle positions for the current rectangles that we have after rotating and permutating these rectangles. Otherwise, if we didn't reach 4 rectangles yet, we can try to swap the width and height of this current rectangle So basically flipping it 90 degrees and then try the next rectangle. So use rotate shape again. And then the other case is when when this rectangle remains as what it is before. So we should just swap this again. Since we just swapped it, if we swap it again, we're going to swap it back. So this is what happens if this current permutation of the rectangles remain as the same. Now we try the next rectangle. So we could also try flipping this 90 degrees or make it remain the same. And for each of these possible permutations, we will try the rectangles again. And this will actually finish rather quickly because here we only have 4 rectangles and the total number of permutations is 4 factorial. And so along with the total number of moves that we have, which is just 2 to the power of 4. So this isn't much for the computer to calculate. Finally, we would have used this check on all of the width and height that we can get. So we would have pushed all of the possible answers into our answer vector, and any answers that have an area less than our minimum area will be cleared out, because every time we will use this clear function. So finally, we can sort the answer and print out the minimum area and print out each of the width and height inside our possible answers. And also here, when we do the next permutation, we should sort our array of rectangles first, because this next permutation stops if you've reached a completely sorted list. So if at first you're not in a sorted list, then the next permutation will miss a few of these permutations for the rectangles, and that way you might get a wrong answer.